Today the topic is M-ary PAM or M-ary Pulse Amplitude Modulated Signal. So PAM stands for Pulse Amplitude Modulation. Pulse Amplitude Modulation. So we would learn the pulse amplitude modulation scheme. We already know from our previous lectures that M-ary, we actually learned the M-ary phase shifting or M-ary M-PSK, where we saw that the phases, we have M phases to represent M unique symbols or M unique signals. Well, we know about this M. M, as I mentioned, this is 2 raised to the power K. So your M in M-ary digital modulation scheme is always 2 raised to the power K. Keep this in mind. Never take M equals 3 or 5 or 7, right? It should fulfill this criteria. So we have in this case integer, you can have K equal to 1, 2, 3 and so on. So you have M, the values of possible values of M are like 2, and then you have 4, you have 8, 16 and so on, right? So these are all the positive values of which is M 2 raised to the power K. In M-ary pulse amplitude modulation, we would see that we have M unique signals, and the signals can be differentiated based on their amplitudes. So actually the amplitude of the signal varies. So if we in pulse amplitude modulation, we observe that the amplitude of the signal varies according to the message signal. So the amplitude of the signals are differentiated by their amplitudes. That is why the amplitude of the pulse. So that is why it is known as pulse amplitude modulated signal. The other 2 fundamental parameters of the carrier, which are like phase and frequency, those will remain constant. So let's start the M-ary PAM signaling scheme. And as we know, let me read it out so that we try to understand each and every line here. M-ary pulse amplitude modulation. In pulse amplitude modulation, PAM, the amplitude of the carrier is varied according to the message signal. So keep this in mind. The amplitude of the carrier varies. The amplitude of the carrier varies according to the message signal. So the message signal is actually embedded into the amplitude variation of the carrier. So the amplitude variation of the carrier will be according to the message bits or according to the message signal. PAM signal can be represented using psi1 of t. Only one basis function is needed, so it is a one-dimensional signaling scheme. So keep in mind, M-ary PAM is actually a one-dimensional signaling scheme, one-dimensional scheme. So keep this in mind. It is a one-dimensional signaling scheme. Let me write it properly so that when you see it later on, you should be able to read it, right? So it's a one-dimensional signaling scheme, and I would write it specifically here so that it's a one-dimensional signaling scheme. It's a one-dimensional signaling scheme. So you have to keep this in mind. It's a one-dimensional signaling scheme. You can represent it only using psi1 of t. So psi1 of t would be used to represent your one-dimensional signaling scheme. Mathematically, you can see the expression. The mathematical expression is very similar to our previous schemes. Si of t is represented by under root 2 e sub I over t p of t cos of 2 pi f c t. So you know about p of t, it's a pulse, right? So p of t, as you know from your previous lectures, that it is actually a pulse which exists between 0 and capital T, and it's a positive pulse. This is your, on the time axis, this is your p of t, right? So this is your p of t. So it means, see, if the pulse exists for 0 to t interval only, and this is multiplied with the rest of the signal, so your signal only exists between 0 to t. So it's the importance of this pulse. If you know that the pulse exists for 0 to t, so your whole signal Si of t actually exists for between this time interval. So Si of t, S sub I of t, can be expressed as under root 2 times E is the energy of the signal, E sub I over t, P of t cos of 2 pi fct. So this is the carrier frequency fc. Well, if you try to integrate it and find the energy of Si of t, you will definitely end up with the expression under root E sub I in this. From this expression, you can try, just square it and integrate it in the period 0 to t, and you will get the energy of the signal, which will be E sub I. The same expression can be written in the in this form. We can also rewrite it here. Now, if you see, P of t is not written in this lower, in the second line of this equation 3.29. P of t, now if we can ignore it, but then we have to specifically write that our signal exists between 0 to t, because we know that this pulse is here between 0 to t. So if you remove that, you have to write here for complete description of this signal, the ith signal. So Si of t is under root 2 times E sub I over t cos of 2 pi fct. And the description is here, that it is between 0 to, for time interval 0 to capital T, and the I, the sub I is from 1 to capital M. So this is an expression for M-ary, pulse amplitude modulated signal. You can also rewrite it as given in the third line, and here recalling your psi I of t, this is written in the form of psi I of t. So you can write it as A sub I psi 1 of t. Psi 1 of t. Psi 1, you know that it is under root 2 over t cos of 2 pi fct. So let me write it for you. Your psi 1, if you recall your previous lectures, it is under root 2 over t. Let me recall. Let me rewrite it again. Let me rewrite it. So your psi of t is actually your psi of t is actually 2 over t cos of omega ct, if you recall it, cos of omega ct. So this is your psi of t, cos of omega ct. So it is written ai times psi 1 of t. Psi 1 of t is 2 over capital T cos of omega ct. So it is written as ai psi 1 of t. Now ai is under root, actually if you see the amplitude ai is under root e sub I. and I is from 1 to m. So we can take the value of m. We can have m equal to 2, m equal to 4, m equal to 8, and so on. So the amplitude AI is unique for each signal Si of t. So you can see that for each signal Si of t, the amplitude is unique, AI is unique, and that is why it is called the pulse amplitude modulation, M-ary PAM signal, while the phase and the phase theta and the frequency FC remains constant. So keep this in mind, that theta and FC does not change. Hence the name PAM. The expression in 3.29, this equation, the expression in equation 3.29 is for M-ary pulse amplitude modulated signal. Signal constellation and the signal waveform for m equal to 2, which is also known as the binary amplitude shift keying. This is also known as binary amplitude shift keying. Is shown in figure 3.12 and figure 3.13 respectively. So shortly we will see those waveform and the signal constellation in these figure. Or let me show you those figures. So let's move to these diagrams, and then we will come back. So if you see the diagram here for m equal to 2, now when you have m equal to 2, you have just two symbols, and the signal constellation can be observed here. You have it is just psi 1 of t, just one dimensional signal, and one of the amplitude is 0. See, one of the amplitude is 0, while the other one is taken. You have S1 0 amplitude, and S2 which is another some amplitude with energy E sub E, with some energy E. So this is for m equal to 2. This constellation is drawn for m equal to 2, and actually this m equal to 2, if you recall it, this M2, this signaling scheme is actually it is applied or it is used in the transmission of radar signals. So we will see it. Let's continue our okay, this was the constellation diagram, and if you see the waveform, the signal waveform for m equal to 2, you can observe it here in figure 3.13. So figure 3.13 actually give you the signal waveform for binary amplitude shift keying, or this is also known as on-off keying. See, you have a signal when you have a signal for some time interval, so you are transmitting some energy, and then you have no signal for the next time interval. So if this is the representation of a 1, this would be 0. Representation of a 1, then you have a 0, and so on. You can continue it. So 1 zeros can be represented by the presence of a signal or the absence of a signal. So you have a presence of a signal, you have absence of a signal waveform, and you can say that this is S1. So we have S1 here in this interval, and S2 is here in this interval. So we have S1 and S2 here. So going back to our text, let's try to continue from where we left. So if we move here, okay, so these binary ASK signal, binary amplitude shift keying signal is shown in figure 3.12 and 3.13 respectively. We just saw these figures. The signal amplitude chosen for binary ASK are either 0 or E. So the signaling amplitudes are either 0 or E. You can see that the signaling amplitudes are either 0 or E, which we just saw in the figure. In the transmission, and this is used in the transmission of radar signals. So radar signals are, you have the amplitude AI is either 0 or E. So AI belongs to this set 0 or under root E. You can see this. And I is equal to 1 and 2. So your M is actually 2. Your M is actually 2. So it's a binary ASK. It is also known as on-off keying because you have a signal. You have an on state of a signal and you have an off state of a signal. So it is also known as on-off keying. So M-ary PAM symbol Si of t can also be expressed using the this notation Si. Just to be consistent with our signal space concept, we can also write our IF signal as S sub I1 psi 1 of t. So it's a one-dimensional signaling scheme. Well, if you have higher values of M, of course you have more amplitude values. For example, 4 when M is equal to 4. When M is equal to 4, then let me move it there. Let me move it to the free space. Let me go to the next slide where we have a free space, and then it will come to this one. Suppose you have M equal to 4 in binary ASK. So your amplitude level, you have 4 amplitudes level. You have you can say SI1, then you have SI2, SI3, and SI4. You will have 4 amplitudes level. And your signal, each signal can be written as SI. This should not be I1. Oh yeah, we can write it like this: SI, SI, or instead of writing it SI1, let me write. Because we have just psi 1, so we would write it here just to be consistent with our previous notation. Let me use a different. Let me use the notation which we have already learned in the previous lectures. I will use the same notation. So when you have AI and your AI is actually your AI is 1i, then you have the second, or instead of I would use 1. You have actually 1 1, then you have 2 1, you have 3 1, and you have 4 1. So you can write your signal as SI1 psi 1 of t. So this would be a proper notation as consistent with our previous knowledge, because we represent this is the image over the first orthonormal, the first basis function, right? So the second subscript, we use the second subscript for the identifying the basis function. So we have only one basis function, so the second subscript in all these symbols, second subscript is 1. You can see the subscript second. The first one is 1 here. Here it is 2. The first one here it is 2. Here it is 3. Here it is 4, which represent the 4 different amplitudes. So we have S11, S21, S31, and S41. These 4 are the amplitude levels of this signal, and you can see that each signal, for example, if I write my signals now, so my signal differs just by their amplitude levels. So you can say that, okay, to be consistent, my S1 of t when we have 4 signals, my S1 of t would be S11 psi 1 of t. S11 is the amplitude of the first ASK, first symbol. Then we have S2 of t, which will be S21 psi 2 of t. Another signal, then we have S3 of t, and S3 of t would be S31 psi 3 of t. Sorry, not psi. This should be psi. Here also we have psi 1, not psi 2. We do not have any other, so let me correct it here. So we have psi 1 of t, S3, S31, psi 1 of t, and similarly we have the fourth signal S4, the fourth unique signal, which is S41 psi 1 of t. So we have just one basis function. If you concentrate here, we have just one basis function to represent all the four signals, and they differ by all the four signals just differ by their amplitude. This is the amplitude scaling version of this psi 1. So all the four signals differ by these amplitudes. So these are the four unique amplitude shift keying signals, and each of these signals differ by the amplitude levels only. So you can think about these signals. You can just choose M8 and M16 or higher values of M. You can choose higher values of M, and you can draw these signals for the. You can have the constellation. You can draw these signals on the constellation, a signal constellation diagram. You can draw their waveforms. When you draw the waveforms, keep in mind the amplitudes would be different for these different signaling scheme. So that is all about the M-ary pulse amplitude modulated signal, and we will see that in our next topic that actually the quadrature amplitude modulation scheme, which is the modulation scheme in the 4G, the 4G of wireless communication, that is actually a combination of M-ary PAM, which is sometimes written as this one. It is a combination of M-ary PAM and M-ary PSK, and this combination is called quadrature amplitude modulation, which you will see in our next lecture.